Sure it's working? Yeah, it is. All right. So last time we were talking about the linked stack. We already implemented a stack with an array. Well, now we're going to implement it with a linked structure. So remember, a linked structure was not a new data structure. It was not a new collection. It was more. It's like an underlying container. It was like it's more similar to an array than anything else. We can use it to implement whatever we want. So we built a stack with an array. Let's build a stack with a link structure. And it turns out the implementation ends up being quite simple, in terms of the general idea at least. We have a link structure. Remember, we have these nodes. And what we'll do is we'll just have, remember with the link structure, we always wanted to make sure we had reference to the beginning, the first node, the node at the beginning. Well, here, that's all we're going to do. So we're going to call that top. It'll be the top of the stack. Every time we want to push something, we just insert to the front of a link structure. So if we're adding that, well, create a new node, throw that in it. The new node's next is what top currently is. And then as soon as we do that assignment, we set top to be, well, the thing we just added. The node, at least, containing the thing that we just added. Adding to the front. And pop, well, that's just removing from the front. Take the element out, and then top equals top's next. So you ask the top node, hey, what's your next? And then we just set it to reference that. And that effectively gets rid of the original, like the node that was at the top. So the implementation idea. If we jump down here, can you see this reasonably well? It's kind of bright and washed out, right? I'll try to lower the lights a little bit. Is that better?
It's better.
It is better, yeah? But how do I look here? All right, nice and bright still. Okay. As always, just to reemphasize, remember we're making a linked stack, but it's implementing the stack interface. The stack interface just describes the what. But when we tell Java we're implementing this interface, we are making a contract that says this thing I'm about to implement is guaranteed to implement everything defined in the stack interface. And if you think, well, but you haven't yet, you're right. And in fact, because I haven't, it's yelling at me. If I tried to compile this, Java won't. It'll say, no, you told me you're implementing the stack interface, but you're not. So I won't. For the time being, we could tell it to be quiet by just doing this. By implementing all the methods. They're clearly incorrect, but these are all the methods that must be implemented to define a stack. Right now, yeah, they're clearly not correct. Like size is returning 0. Is empty always returns false. That's not right. But at least it shuts up Java for the time being. But we're going to go and implement these things. We did the same thing with the array stack. And what's kind of cool here is by implementing the stack, and we're going to see more of this in a moment, but by implementing the stack, the array stack and link stack are both stacks. Anything I can do with an array stack, because it's a stack, I can do with a link stack, because it's a stack. And we are guaranteed that they are stacks because we said implements stack. If we didn't implement stack, we could still use these things as a stack, but then I lose a lot of fancy power that I get with this idea that we will see throughout the rest of the course, and I'm going to try to emphasize at the end of this topic as much as I can at this stage. But here we go. What do we have as fields? We'll have two fields. The node at the top. By the way, if you're wondering why I'm moving so fast, it's because we did this on Friday, and I just don't want to waste too much time on it again. We've got the node at the top. It's just a reference variable to some node. And int size. Size is going to be the number of things currently in the stack. The constructor, we're only going to have one. Because remember with the array stack we had two. We had that default one, and then one where we could specify an initial capacity. Here, initial capacity is not really a thing. There's really no need for a second constructor. So here it is. And what does it do? Well, it creates an empty link stack. And what would the state of an empty link stack be? Well, size should be 0. and the top should be nothing, null. Any questions so far? This is just setting up the fields and starting the class. We haven't implemented really anything yet. All right. Great. Push. All right, so what are we going to have to do? Well, with the array stack, we always had to check for that capacity issue. Have we run out of room in our array? Fortunately, that's not going to happen to us here because that's not a thing with linked structures. We're not bound by any capacity. Suppose if you want to be like, well, technically there is a limit in the amount of RAM and space on your computer. Fine, but we're not getting anywhere near there. So what are we going to do? Well, create a new node. The new node is going to store reference to the data we're pushing. Because the node isn't the data. The node is going to be that little container for the data. And not only does the node hold reference to the data, the element in this case, but it also holds reference to the subsequent node. So, uh-oh, someone's phone. Who do we make fun of? It was you. You know, if you didn't say anything, I wouldn't have known where it came from. You took care of that really subtly. Well done. Anyways, what do? So, we create a new node with the data in it. We set that new node's next to be top. Now, top could be null, or it could be a reference to some other node that was the top, or at least the top the instant before I call push. So I set the new node with the new element I'm pushing next to be top. I say, well, top, hey, the field top, that reference variable to the node that's supposed to be the top, now references the new node we just added. And increase size +1, and then return true. This particular one is always going to return true because it's not really possible to fail in this particular example. But that's it. That's all pushes. That's adding to the front of a link structure. That's the code for it right there. Any questions about push? Remember, if you have a question, chances are half a dozen other people in the room have the same question, so now's a good time to ask. The number of times, and look, I never want to discourage someone coming up after lecture when someone has a question, but the number of times people come up after lecture, this happened on Friday, they come up and ask me a question after lecture, and I'm like, why didn't you ask that during lecture? Because 2 other people just lined up with the same question. So, you know, do them a favor. Ask the questions when you have them. Really? No questions? Yes?
Do you have to create the node in the class yourself beforehand?
Yes, this is assuming, good call. This is assuming the node class exists. Now, we're actually going to see something interesting at the end of this topic about the node class specifically, but this assumes we already wrote that node class that we talked about, I think, in the previous, if not one of the, like a topic just before. But yes, this assumes a node class already exists. Good catch. See, look what happens when someone asks a question. Wasn't that a great question?
Yes.
Yes, it was a great question. All right, pop and peek. Let's jump down to peek because it's a little easier. Well, what do we want to do if we peek from an empty collection? Well, just like the array-based stack, if it's empty, we'll throw an exception. Why? Well, should someone have, like, is it really a reasonable state to, like when I call peek, when someone calls peek, the expectation is they get something back. But when it's empty, what do you get back?
No.
We could do that. We could. But you know, the expectation is that we get something back. We get something of type T back. But in that case, that wouldn't be happening. So it's kind of like the unusual. I would be surprised if I called peek and didn't get something of type T back. I want to be clear. Getting null back would be entirely reasonable as an option, as an implementation option.
Depends on how you want to use the
Bingo.
stack.
To conform to really what the standard library does, we're going to raise an exception because that's an atypical, exceptional situation. You know, it's empty. You're going to get something back that doesn't really make it. Let's make it an exception. If someone calls peek on an empty stack and they see an exception, they can manage that how they see fit. Did they misuse the stack? Maybe this is fine for weather purposes and they just deal with it as they see fit. Fine. Otherwise, just get the data from the top. But remember, peak just returns the data. It doesn't modify. It has no effect on the stack. It doesn't alter anything. It just observes it. Pop, on the other hand, is the same idea, but in addition to returning the element, we want it removed from the stack. So, check if it's empty. If it is, throw the exception. Otherwise, get the data, set the top to tops next. That's removing from the front of a linked structure. That's all that line of code does. Decrease size, and then return the data that we just, got out. Why is it important that I stored the thing that I wanted to return before calling this line of code? Who can tell me? It's not a trick question. It's not an overly sophisticated answer. I'm just curious.
Because if we get rid of it beforehand, then can't get rid of it.
Yeah. If I got rid of it, imagine I said, okay, the data I want is in top. Is in the thing that the reference variable top references. If I come along and I say, okay, top equals top, dot get next, okay, great. There was a node here that's now just kind of floating in limbo, and I say, okay, get the data from that node. You're left going like, well, how? I have no reference variable to it anymore. It's gone. It was obliterated. I can't get that data out of that node anymore because I have no way to get to that node anymore. So it's just important that we save it beforehand. And then, return the element after decreasing size. Any questions about pop and peak? You don't? Size, well, return the size, because we always just update the value of size. Is empty as well as size 0. That's all. ToString, well, here's ToString. Now, you might remember, with the array stack, we did our ToString in a way where we had a design decision to make. When we wanted to print out the stack, when we wanted to create a string representation of the stack, how did I want that string to look? There is a top of the stack. Do I want the top of the stack to be at the beginning of that string or at the end of the string? Both are fine. One's not more correct than the other. It's entirely up to us. But how did I want to represent that string? That was a decision I had to make. And I decided in my implementation, I want the top to always be at the very beginning of that string. So what I did is when I built the string, because the array is ordered such that the bottom of the stack is always at index 0, and the top is always at the other end, I couldn't start at index 0 and start building the string from index 0 to index 1, 2, 3, 4, because that would mean the top is at the end of the string, right? So what I did is I kept inserting into the front of the string builder. I always took the next thing and prepended it to the string. So the top was at the front. But here with the linked implementation, the top is in the node at the front. I don't need to do any prepending stuff. I can start at the node at the beginning and keep appending every subsequent node's data to the string, so that it conforms with the expectation that the top of the stack is at the beginning of the string. So here all I do is create a string builder, and this is iterating over a linked structure. Create a node, call it current node. Well, it's not null. Current node data, append that to the string builder, append a comma, and then current node equals current node.getNext. So this is just iterating down a linked structure. Once current node does equal null, it stops iterating. And then we just get the string builder's string. Any questions about this? This is now where review stopped from Friday. We didn't talk about ToString for the linked stack. So any questions, ask away. It's important to ask. It's boring when I just talk at you for an hour. what would happen? No.
Oh, come on, ask it.
All right. What would happen if I did that prepend thing here, where I kept inserting to the front of the string builder in this particular case? What would the string look like? It would be just reversed. Yeah, absolutely. That's all. It wasn't a trick question. It was just, what would happen? Well, it would, instead of building the string by keep adding to the end, I just kept adding to the front. So the order would be in reverse. Equals and hash code. Well, this might look hairy, but trust me, it's not. Are they literally aliases? If it's null or they're not even the same class, return false. Otherwise, cast a thing. This question mark here, we haven't seen that yet, have we? But we can see that it's clearly in the context of a generic. What it means is it's a wild card. I could put a T there, and that means it would try to cast the linked stack to something that's holding on to things of type T. But it's possible that I want to check the equality on a stack containing integers and a stack containing strings. It's not going to be equal. But maybe I really want to do that. I don't know. Or maybe the thing of type T is like a superclass or subclass, which is this whole idea of inheritance that we haven't covered yet. But the point is, I don't really actually know what's in that stack. So I throw this question mark in there to be the wild card. It just means the thing I want to compare to is a linked stack containing elements of some type. That's what it means at this point. So I'm saying, oh, you're a linked stack containing some elements. I check if their sizes are the same. If I have a stack of size 10 and a stack of size 20, are they going to be equal? No. I don't even need to look at the contents. If they're not even the same size, they're not equal. Done. So far, so good? Then what? Well, I create a this current and a that current. These names are just names, doesn't really matter. But it's this tops and that's top. This is this current object, that is the one I want to compare to. Now, because I know these things are the same size, really I don't need to have a check on the null on both, but I'm going to. Well, this current is not null and that current is not null. Check the contents. If objects equals this current data and that current's data. If they're not the same, return false. If they are the same, keep checking if they're equal. And then as we move down, this current is this current's dot get next and that current's. The trick here is we're iterating over two link structures at the same time. So we have two reference variables that are iterating down the link structures as we go, one for each of the link structures. That's why I have a this current and a that current. And if we ever get to the end and have not returned false, I can of course therefore conclude that they are in fact equal. Now, a moment ago I was saying this check right here, the and that current is not null, is not necessary here because I know the linked stacks are the same size, and I know they're the same size because I just checked that on line 82, is it? 82? Yeah. Because I know they're the same size, I can always just check if this current is null, because every time I set both to next, it's gonna be fine. But what's the harm in checking if both are null? It's very defensive. It's good to go. So any other questions about, or comments, thoughts, concerns, observations about the equals for these linked stacks? Now, what's kind of cool here is the contained elements type, that question mark, it doesn't really matter if they're different types as far as this equals is concerned. It's the equality check, like the object.equals, that's going to check the equality between the two elements. So the question marks, I'm checking equality on the stacks. someone else is going to check the equality on the contents of the stacks for me so I can make the decision on the equality of the stacks. If they're both integers, for example, the equals will tell me if those two integers are equal. But if it's an integer and a string, well, when I ask objects.equals, it's going to call the equals for those types, and if they're not equivalent, it's going to be false. So it's actually not my problem as a linked stack to care about the types equality, the generic types equality, because that is delegated to the types equality definition, the integers equality, the strings equality, whatever it is. I ask it, it tells me true or false. I use that information for my equality for the stacks, but it's not my problem to know what the equality is for the underlying type, the generic type. This whole idea of delegating responsibility is critically important for good design here. Hash code, just iterate over and hash each of the elements as we go, that's all. And remember, like we were saying, don't worry too much about hash code. The whole idea is if they're the same, they should have the same hash code. If they're different, we really want them to have different hash codes. Now, the node class. We defined that last week sometime. We public class node, it's generic, has two fields, data and next. Had some constructors, it had a get next and a set next. And it was interesting because we made an observation that that class is mutable. I could maybe change it in such a way, maybe I really don't want it to be mutable, I don't know, but the node class is mutable for better or worse. And you will say, well, you've kept making a big emphasis on not, make your stuff immutable. But the node class is mutable, and that was by design. But here's the thing. Now I want to be clear about what I'm about to say. What I'm about to say is not a requirement. If you don't do it this way, you're not making a mistake. It's not like you're not making a fundamentally incorrect decision. But there would be a lot of people that will tell you that, although it's not wrong, it's wrong. So here's the thing about the node class. The node class itself isn't important. It's not. It's important for the linked stack, because the linked stack uses the nodes, but it's not important elsewhere. So the whole idea of this node class is really important for the underlying implementation of the linked stack, but nothing else yet, at least. It's not like this class I'm going to be using everywhere. It's important for the linked stack implementation, but it's not just, I'm not going to just start in main creating a linked structure for no reason. I could, but I'm not going to. And on top of it, you might remember at the end of the linked structure topic I talked about a doubly linked structure, right? There's nothing stopping us from having a node where you have a predecessor in addition to a successor, like a next. We could do that. There's a little bit of extra bookkeeping we have to keep track of, but there's nothing stopping us from having a reference variable to a predecessor. If I wanted to make a class for this, what would I have to call this class? Let's assume for a moment I already wrote a node class. So what do I call this? Doubly linked node, I guess? Maybe then I should, because I got a doubly linked node, maybe the original class should be called like a singly linked node. But they're both nodes. Really, I would like to just call them both a node class, but I can't have a node class defined with two links because I already defined the singly linked nodes. I've got this namespace pollution thing where I've got this node class, and maybe I want another node class that has a slightly different implementation, but I can't have them both exist in the same package because then you have a name conflict. That's the whole thing. And additionally, it's not important for anything really. It's only important for the underlying implementation of the link stack. The node is only used in the linked implementation so far. So as far as the user of the linked stack is concerned, do they give a shit about the node class? The user doesn't. You, as the author of the linked stack, obviously has to care. But if I come along and use a link structure, I don't want to think about a node object. I don't want to know. I don't know. I don't want to know. Don't give me more details that don't matter to me. I want to get in my car and drive. If you make me have a lesson about how internal combustion engines work before I can get in my car and drive, I'm going to be really annoyed. Sure, it might be interesting, but I don't care. I just want to drive my car. I want to go home after work. I want to get to work. That's all. So I don't know. I don't want to know about those details because they don't matter for me. And this information hiding, this idea of information hiding, is important for good design because you don't want people to have to know about things they don't need to know about. And you don't want people using things that they shouldn't be using because that's a recipe for disaster. So having good control over how and when and where things are accessed is a good thing. So this is a similar idea to expand capacity, right? Where expand capacity was just a method. It was a private method that the array stack had, and same with the course class and the country catalog and the friends class. It was a private method that no one needed to know about that method, but it was an important method for the internal functioning of the class, right? So it existed within the class, but it didn't need to be known about elsewhere. But that was only a single method. Now we're talking about a whole class. This whole node class. It's important for the internal operations of a linked stack, but it's not important outside. So what we do is we take that same idea, the exact same idea we had by making that method private, we can make a whole private class and put that class inside the linked stack. This is called a nested class. So, okay, we're going to put it inside the linked stack. Instead the node class puts inside, yes. So if this is done, the node class can still be accessed perfectly fine within the linked stack class. But it's only accessible from within the linked stack class. So it keeps the node out of the way of every other class that we have in our project, which is kind of nice. Okay, so nested classes. So we're going to put this right here. First, note that I'm not going to get into the details of all the different types of private inner classes. But you can have a private class, you can have a private static inner class as well. But this here is a private static class node. And it's actually inside the linked stack class. It is identical to what we saw before. The difference is this is going to be internal, and it's private and static. And if I go here and click linked stack, and let's open it up real quick, you can see, there it is. It's right after hash code. Whoop, wrong way. It's contained internally. I can use it as if it wasn't internally. Like the syntax and how I use that class doesn't change. It's just the only noteworthy thing here is that I've tacked it on inside of the linked stack class. And it's private. It's important for the internal functionality of the linked stack, but it's not important outside. And I don't want anyone else to worry or think about the node class. They don't need to. Don't burden them with information they don't need to know about. Just like the expand capacity. It was private. They didn't need to know about it. Here, it's the exact same idea. It just happens to be a whole class, not just a single method or a suite of methods. So it's kind of cool. Now, if you hate this and you think, no, I would never make an internal nested class like this, I don't like it. Fine, you don't have to. You should though. It's better design, but it's not a requirement. But I think that's pretty cool. Any questions about this at all? Yes?
Why specifically is it static? I know you said you weren't going to go too into it.
Honestly, I can't remember right now. I'm trying to remember right now. There's a difference in what we call them. One means we can access everything from the external class directly, and the other one we can't. I might even be getting that wrong right now. The point, it really doesn't. Let me put it this way. The fact that I can't remember right now should not be indicative of, oh no, he can't remember. What it is indicative of is that's how much it matters to know the difference at this stage. Let me put it that way. Here. Let's see. Inner class and static nested class. Let's see the difference. Static nested classes are accessed using the enclosed class name. Okay, yeah, but you don't need that. Okay. Terminal nested class, common preference, province, nested inner. Organization, access, convenience. There are 4 kinds of static. You know what? This is taking longer than I wanted. Point is, it doesn't matter too much right now. Just do it that way. And when we need to find out, we'll look it up later. Deal? Now, here's the cool thing. If we go back here, actually no, let's go back. Down here, you can download this link stack playing code, which is verbatim this. Playing link stack, it's just a main method, and it's making use of a link stack. And there's code to do a couple of things here. It's just playing around with it, calling the methods to show you that it works. I mean, there's obviously the unit tests for it, but it's always, sometimes, manual tests are a little bit more interesting. So what do? We create a stack. We use a stack reference variable called myStack, and I make a new linked stack. I say myStack.size because every stack has a method size. Every stack has a method is empty. Every stack has a method push. Every stack has a method pop, and so on. Right? I'm just calling the stack methods. Right? And then I'm trying peek on an empty stack, and I'm catching an exception, and I'm printing out the stack trace, whatever. I'm just using the stack. If you go back to the array stack topic, at the end of that, you will find another download file called array stack playing code, or whatever. And below that link is code that looks exactly like this, but one difference. One line of code. Not even one line of code, half of one line of code is what differs. The only thing that differs is which implementation am I instantiating? Which version of the stack am I actually creating? What version of the stack am I actually creating here? Someone tell me. Linked. And you can tell because line 6, that's line 6, right? From my angle, it's hard to tell, actually. Just FYI, if you're wondering why I'm bad at the line numbers. Line 6, yeah, that's much better. It's a linked stack. Why? Well, the right-hand side says new linked stack. That means go to the constructor for linked stack and make the linked stack. And then that constructor returns a reference to the linked stack it just created that gets stored in the reference variable for my stack. What is the type of that reference variable? Integer. No. What is the type of the reference variable? That's the generic type. This is not a trick question. It literally tells you right there. It's not integer. There's a hint. Stack, thank you. Who here didn't say stack because they thought it was a trick question? See, I told you it wasn't a trick question. It's a stack. Now, I want to be clear. I could have made that reference variable a linked stack. I could have made a linked stack reference variable, and this code would work just fine. But if I did that, I wouldn't be able to do the following. If I wanted to change out the underlying implementation that I'm using for the stack, all I have to do is go to that line of code, line 6, go to the right-hand side, next to new, change link stack and put array stack. And I can hit run, and this is guaranteed to work perfectly. Because the implementation doesn't matter as long as they're both stacks. Every stack I can push, I can pop, I can peek, is empty, size. Stacks are guaranteed to have that as defined by the interface. And because the array stack and the link stack both implemented the interface, I'm guaranteed that those have them. If I didn't implement them, if those implementations didn't implement the stack interface and did still have those methods, Java wouldn't let me do that though. Java wouldn't let me call isEmpty, side push, and whatnot with a more high-level abstract reference variable like stack. Because there's no guarantee. I know they're there, you wrote them. But Java can guarantee that they're there because you implemented the interface stack. And it wouldn't compile unless you implemented all of those methods. So by implementing that interface, you can already eliminate a lot of potential issues in your code. You can guarantee that all of these methods exist. I can go and change out the entire implementation, the entire underlying implementation by changing half of a line of code. If I made the reference variable a reference variable for a linked stack, I couldn't say linked stack, my stack equals new array stack. It wouldn't let me do that. Because although they're both stacks, the reference variable has to be something that is a linked stack. And you're trying to give it an array stack, so it's not happy. But both an array stack and a linked stack are both stacks. Which is pretty cool here. So the reference variable is more general than the actual thing it references. That is one of the several benefits that interfaces give you. It's really cool. Are there any questions about that? If I told you to do an assignment, maybe I'm going to do this year. Assignment 2, you need to use a stack, and I say you have to use an array stack. Right? Or I tell you to, I don't even think I actually specify which version I want you to use, but I think I give you an array stack in the handout. But if I were to say to you, the day before it's due, no, you got to use a linked stack. If it takes you more than 3 seconds to make that change, you've done something wrong. Because all you should have to do is change half of that one line of code. And then boom, done. It's now using a linked stack. I'm not going to actually do that. But if I did, and if it takes you more than 3 seconds, you've done something wrong. Any questions, thoughts, concerns, problems, observations, musings? You know? All right. Algorithm analysis. We have very briefly, very high level talked about this idea several times last semester and this semester. But now we're going to talk about it a little bit more formally. It's still going to be kept very high level, but we can keep it pretty high level and still get the gist of what's important here. What does it mean for an algorithm to be good? Someone submits assignment 1, another person submits assignment 1. They both work. But is one implementation better than the other?
Yes.
How would it be better than the other? What would make it better?
Less lines of code means that it would run faster.
Potentially. Probably not in practice, but potentially. What else could make one algorithm better than the other?
Redundant lines of code.
Redundant lines of code. Okay.
It might, use shorter processes to do the same thing.
Like it just somehow take less time to do the same thing. Yeah? What else?
The code is easier to read.
The code is easier to read. That's a big one, right? Good variable names and whatnot. Yeah. On that note, something I should have said last week on the midterm. I was nice when marking this one. If people had bad variable names, like A equals blah 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 and B equals blah 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 blah, then you're using A and B. The next test, no, I'm not. I'm gonna rip you to shreds if you do stuff like that. Code understandability is a metric. It's a very important one. What else? What else could make someone's code better than someone else's code? The amount of memory it uses? Yeah, that's a good one too. In fact, yours is similar-ish to what he said over there too, was kind of like the resources that the code needs. Another thing might be how robust it is to change, how easy it is to refactor, to update it, to do something slightly different. There's a lot of different things, but what do we care about? Sometimes people might start geeking about lines of code. They might start geeking out about how clean their algorithm is or whatnot, right? There's a lot that we could care about. But one of the most important metrics we care about is the resources that your algorithm needs. Things like lines of code or redundant lines of code affect the resources, right? But those might have some small impacts. There are some ideas and some things that have way bigger impacts. So one of the questions we might ask is, here's an algorithm. Right? Do you remember me talking last semester about the traveling salesperson problem? Right? You have to visit all these different cities. You start in Antigonish. You need to visit a dozen cities. You start in Antigonish, you want to end in Antigonish. How do you visit them? Do you go from Antigonish to Yarmouth to Cape Breton to Halifax to New Glasgow to Truro to Port Hawkesbury? No, you're doing a lot of backtracking and whatnot. That's a bad one, right? You'd want to have a better pathway. But if I told you I want you to write an algorithm to find the best path that would take the least total distance, what would you do? The algorithm is trivially simple. Calculate the distance of every possible configuration of those cities. Pick the shortest one. Would you agree? No?
It's with that kind of a problem, you'll always end up with it's a factorial pretty much for time.
Well, the point I'm making is that algorithm is correct.
Yeah.
It's just time efficient.
It is entirely impractical. You can't use that algorithm in reality because the amount of time it would take to do that is hilariously long that it would take. There's more configurations of 100 cities than there are particles in the universe. I'm not joking. You could take each particle in the universe, assign one of those configurations, and you'll run out of particles very quickly. That's how many there are. It's insane. So you're not going to be able to do that. So that would be a very impractical algorithm. In spite of its correctness, it's not feasible. So some of the questions that we might ask is, how much computing resources does it need? How much memory does it need to use? How many processors does that algorithm need to use? And perhaps most importantly of the things that connects these is how does the amount of resources required, those respective types of resources, how much of those resources required change relative to the input size? That's, for example, like a linear search. If you have 10 things, and I want to check, does this element exist in that set of 10 things? How many things do you have to look at? 10. What if it's 20 things? How many things do you have to look at? What if it's 100? What if it's n? What if it's 2 times n? That's an example of, well, the amount of resources it requires. How does it change relative to the input size? Well, it changes linearly. If you double the input size, you double the amount of resources it needed. So it's not the absolute values, it's how does it change as the input size changes. That's a very important aspect of this. Now, we're going to focus on time complexity. The other ones are important too. Space complexity, that's like memory. How many processors it takes, those are also very important as well. But we're going to focus on time complexity because it's a very important one. How much time an algorithm needs relative to the input size. So how long does it take to sort 10 items versus 10,000 items? The trick with the sorting, unlike the searching, sorting takes a lot more time than just searching. The relationship typically with your sorting algorithms depends on the algorithm. It depends on some constraints that you may or may not care about. But with searching, the linear search grew linearly. It was a linear search. With sorting, the amount of time, it won't grow linearly, it'll be worse. If you double the input size, you might quadruple the amount of work you need to do, for example. So, when doing time complexity analysis, we consider how many operations are required for that algorithm. And a simple operation could be like an addition, a comparison. Doing one of those additions is like 1 unit of work. Even though, like for a computer, doing addition is a couple more steps than just 1 unit. But for the point here is the amount of time it takes for an addition really doesn't change relative to anything. Adding 5 and 5 and adding 20 and 20 takes the same amount of time. There's no real scaling there. It's not like searching, where, well, it depends on how big it is. Now, mind you, when you start to have really big numbers, okay, that's not necessarily true, but for our purposes, all additions take the same amount of time. Comparing two things takes the same amount of time. And the important thing here that I really want to emphasize is it's funny. People will show up in first year programming or something, and they'll show up like big shots because maybe they spent a couple of years programming before. But 99 times out of 100, they have no concept of this, complexity analysis. And this, not necessarily bad, you could probably survive without it, but when you have an understanding of complexity analysis, it better equips you with making decisions on what algorithms and strategies that you should take to solve certain problems, because it's going to be way better or way worse, for example. So complexity analysis gives us the ability to make informed decisions about our code that we would otherwise just not have. All right, we'll pick up here tomorrow.